Okay, let's go ahead and get started. So good morning, everyone. Last time, just to briefly review, we were introduced to the transport layer. So as you recall, hopefully, in the first few weeks of class, we talked about the application layer. And now we've moved down the stack to talk about the transport layer. And below the transport layer is the network layer, which we'll cover after next week. So we covered the transport layer. Can anyone remind me what the functionality of the transport layer is? What is its goal? Anyone? Okay. Exactly. So the answer was to allow applications to communicate with each other as if they're directly connected. Yeah, so that's exactly right. So it's to provide this seamless end-to-end communication, all right? So now, are there any questions over the homework that I assigned you guys? Okay.
So for the first one, if you put a reliability service on UDP, what I get from last class is in the transport layer there's no possible way to add reliability, but you could possibly do that in the application layer specifically if you want it.
Okay, yeah, all right, so the question asks, well, suppose you're using UDP for transport, and UDP doesn't provide reliability, right? So could you make a reliable application on top of UDP? And the answer is definitely yes, because your application could keep track of these reliabilities, the reliabilities of sending and receiving messages. And the first thing we're going to talk about today is different ways to actually ensure reliable delivery of packets. And so your application could actually use any of these methods. Like all these methods, today we're going to talk about just general concepts, reliability and flow control. And these concepts could be implemented at any layer in the stack, okay? So below this, we have more layers, the link layer and the physical layer. And we could provide reliability at any layer in this stack. And so suppose we provided 100% reliable network down at the physical layer. So any functionality that's in this layer is passed up the stack, okay? So if you build your application on top of a reliable transport layer, your application gets that reliability for free, all right? So that's the purpose of this layering, is so that we can provide functionality at one layer and everything up the stack inherits that for free. All right, and this also allows us to implement things at the most, the layer where it makes the most sense. So we'll see that the reliability and flow control, they're implemented in most protocols like TCP at the transport layer, and they're implemented there because it really makes the most sense to put them there, okay? Because we don't want to have to write the same functionality for every different application, and we can't really push it into a lower layer. So we want to put things at the lowest layer possible so that everything above that enjoys those benefits. All right, so I just wanted to cover this because there seem to be a few issues with this layering. All right, so don't get too confused about the layering. It's just a way to divide up the design space to make it easier for us to understand and easier to build. All right. All right, so as I mentioned, today we're going to talk about these two concepts, reliability and flow control. And each of these are generally provided in the transport layer, but you could provide them anywhere. All right, so before I get into the discussion of reliability, we need to define one term, and that is, what is a buffer? A buffer is simply, we can call it something like a bucket that holds packets until a system is ready for them. So we're going to use lots of water analogies today. So to give you an analogy to a buffer, a network buffer, is we can think of just a bucket of water. And this is actually a buffer. It holds our water until we need it, and at which time we need some water, we can remove some. All right, so this is a good analogy for a buffer. Is there any questions over that? Hopefully this should be a simple concept. Okay, let's move on to reliability then. So what do I mean by reliability? Does anyone have a guess at the definition of this? Someone besides Clarence? Okay.
You can kind of place your trust in the system that it'll do what you're asking.
Okay, so place trust in the system. Let's say that we're just confident that any message we send will be delivered. All right? Now, if you recall from last time, the network layer provides only best effort delivery. Right? So it does not provide reliable delivery, meaning that whenever we put a packet into the network, we're not sure whether or not it'll be delivered. We hope so. The network will try its hardest to deliver it, but it might drop it. So why might a network device drop a packet? To see that, you need to understand what buffers are and how data moves through the network. So suppose we have a PC here that's sending to some router, and then the router forwards it on to the destination. All right? Well, the way that the packets can be dropped in here, the way we can have unreliable transfer, is that this picture actually simplifies it a little too much. We need to add the buffer into this picture. So this router has a buffer here. The incoming packets are buffered here. So I'm going to draw them like this. Each little slice is a packet. And these packets are buffered until the router is ready to write them to this outgoing port here. All right? Until it has enough bandwidth to place this packet over here, then it's buffered in this queue. All right? Now, so the way that errors occur in the network is that this buffer fills up. And then another packet comes down. Draw it like this. So another packet comes down. It tries to place in this buffer, but the buffer's full, so it's just dropped, okay? If the buffer's full, then this router just throws that packet away, all right? It totally ignores it. So meaning that there was unreliable transfer, right? This message did not go through the network. All right, so this is the cause of unreliable communication in the network. And the reason this buffer could get full is that we actually have multiple ports coming into this router. So we may have multiple machines here. And they're all sending traffic that is also going out this link. So this is a scarce resource. Here, this link is a scarce resource. And so the buffers of incoming packets can get full, and then packets are dropped. All right. So are there any questions on this? All right, so now that we understand what a buffer is, what we actually want to be doing here to ensure reliability, let's talk about some ways to actually ensure reliable delivery. So does anyone have any ideas? what's one way we could guarantee that our messages get there? Okay. Yeah, exactly. That's great. So one way is we send multiple copies. Okay. All right. So we'll ask, I'm going to translate that into the terminology that networking people use, which is called an acknowledgement. Okay, so you ask for an acknowledgement. All right, so does anyone have any other? Yeah. Okay, that's actually a really good answer. So make the buffers very large. Okay, so these are pretty much the only three ways to do this reliable delivery. And so let's analyze each of these real quick. So if we send multiple copies, are we guaranteed that the message is going to get through? No, we're not guaranteed, right? But we can send as many copies as we want to push the probability of success to, towards 1, right? So we have here that the probability of a successful communication is equal to, we have 1 minus the error rate in the channel divided by the number of copies sent. So this means that if we were to plot this, we have success. This is the probability of success over here. This is the number of copies. This chart, and this is 1. Then this chart looks something like this, where in the limit we approach 1, but we never actually reach it. All right. So with this method, we can be probabilistically ensured of delivery, but we can't actually 100% guarantee it, right? Okay, so now this ask for an acknowledgement. So let me draw what this looks like. And these are the type of pictures that networking people use. And on the left here, this line indicates the data that's sent or received from the source. And this line represents the destination. And then as we move down this diagram, this is going to be time. Any question?
Yeah, sure. Just for the P success, is that just we just need 1 copy to successfully send it to, or what are we calculating?
Oh, okay. So the question is, what exactly are we calculating here? This is the probability that your packet, if you sent this many copies, let's just say this is 10, for instance. If you send 10 copies, this is the probability that one of them will make it through.
Then shouldn't the formula be 1 minus error rate exponent?
Yeah, it should actually be that. Okay, sorry about that. Right, so all right, so sorry, this is it's the error rate, yeah, error rate raised to the exponent of the number of copies, right? Sorry about that. Okay. So correction there. By the way, you don't necessarily have to know exactly what this probability is. Just have a good intuitive understanding of it. All right, in this class, we're not, this is an introductory class. You guys are non-majors. We don't really care if you understand all the math and everything behind networks. We want you to have, understand the concepts. All right. Anyway, so moving back, let me move this over in our diagram here. So as we move down, we're going down time, okay? And so if the source sends a packet, and this is the way we'll draw these packets, is that, so we're moving downwards in time. So this is the start of the transmission here, and then this is the end of the transmission. All right, so let me label these. It's the end. So this is the amount of time it took to write that one packet onto your outgoing interface. So it either sent it across the wireless network or on something like an Ethernet network. And then this is the time it took to begin reaching the destination, and then right here is when it was completed to the destination, okay? So what happens now is we send a packet, and the destination acknowledges that packet. This is the ACK. All right. So now we've implemented this. We're asking for an acknowledgement. So whenever the source sends a packet, the destination sends an ACK. And then the source knows that its packet was delivered in time. So what happens now if, for some reason, during communication, this ACK is lost here? So ACK is dropped. Now what should we do? Okay, so we should resend it, but how do we know when to resend it? Or, okay?
You got the source and an acknowledgement request.
Okay, so the source could then,
Like after a certain time.
okay, so yeah, so that's what I'm looking for. So after a certain time, the source can send another request. So they could send an acknowledgement request, okay? But the hard part about if we just sent an acknowledgement request, we're not sure whether our packet was dropped or the acknowledgement was dropped, right? So instead of sending just an acknowledgement request, let's actually just send the packet again. Okay. All right, and then so this time, oops, I drew that a little big. This time, let's suppose that the acknowledgement makes it through. Okay? So this idea of waiting for a certain amount of time to retry, this is called a timeout. All right, so a timeout is just equal to some amount of time which after this amount of time, we assume that the packet had not successfully made it to the other host. We assume packet was dropped. So can anyone tell me a problem with using timeouts to detect failures in the transmission? Okay.
It'll take a long time.
Right, so it'll take quite a bit of time, right? Because we have to set our timeout value long enough that we could have received the acknowledgement if it was actually sent. So we have to sort of be able to gauge this to make it long enough but not too long. So it's kind of a tricky trade-off, all right? Yeah.
How do you gauge the timeout? I mean, the time it tends to send and receive is going to vary based on where your destination is, right?
Exactly.
You have to have one successful acknowledgement sent before you can gauge an adequate, the optimal timeout.
Right, okay, so yeah, the question is how do you set this timeout? Because you have to make at least one successful communication to get what's called the round trip time. So this is another definition we need. And the round trip time is equal to the time for a packet to be sent it's the time it takes for the packet to reach the destination and for the destination to reply. So I will abbreviate acknowledgements with ACK. Okay, this is very common in the networking world. As you can tell from the earlier classes, we really like acronyms and shortening things. So hence use of ACK. Yeah.
Isn't the round trip even kind of variable? Like what happens if the acknowledgement gets buffered for a while?
Exactly. So the question is, isn't the round trip even variable itself? And the answer is yes, it is. We'll talk more about that later on. For now, you can just assume it's relatively the same. All right, so this amount of time, let me do this in a different color. So this time to send this packet down to here when we receive the acknowledgement, this is the round trip time, which we'll abbreviate RTT. So this is the RTT between this source and this destination. All right, so now going back to our timeout values, we need the timeout to be at least the round trip time, right? Has to be greater than or equal to the round trip time. Otherwise, we'll just assume that every single packet was dropped and we'll never actually send anything. All right, so now there's been a lot of work going into, well, you can dynamically set these timeouts. So one thing is you initiate communication with a destination, you measure the round trip times, and you can dynamically adjust your timeouts. We won't go into any of that detail. I mean, there's a lot of work in just that area, all right? All you need to know is this, that your timeout must be at least the round trip time. Okay. Yeah.
So, for example, if it says packet 1, that the acknowledgement is dropped, and then it sends packet 2, and then, I mean, like, sends packet 1 and it went to the buffer and waited for a while, right?
Mm-hmm.
And it sends packet 2 afterwards, and the arc for packet 2 was dropped. And
Okay.
after the arc for packet 2 was dropped, the arc for packet 1, actually went back to the source.
So, okay, so hold up. We'll get into, so you're getting into some like more like details of the protocols and stuff. We'll get into that level of detail, but not yet, okay? All right, so hold on, and we'll come back to that. All right, so does everyone understand timeout, round trip time? Should be fairly easy concepts. There is another way that we can avoid this, delays of timeouts. And that is to use what's called sequence numbers. So now we have the same setup. We have our source, we have our destination. Time is going down. So now when we send a packet, let's assume that we label it a number. So this will be packet 1. All right? And then whenever our destination acknowledges a packet, it includes the sequence number of the packet that it's acknowledging. Okay? So now we don't have to just rely on timeouts to notice if packets didn't arrive, because we can do something like this, where we send multiple packets before receiving any acknowledgements. So this is packet 1, or this is 2. This is packet 3. I'll color in these lines so that it's slightly easier to understand this. And then when the destination acknowledges, it does what's called a cumulative acknowledgement. And this cumulative acknowledgement just has the number of the highest, has a sequence number of the highest packet you've received. So here we ACK packet 2. Let me use different colors for this. Here we ACK packet 2. And here we ACK packet 3. So that way, if we suppose we keep sending some more packets, and actually let's suppose that this one doesn't make it. So now we send packet 4. And this is packet 5. So when the destination here acknowledges it doesn't acknowledge packet 5 because it hasn't seen packet 4 yet, all right? So when it sends its ACK back, it only acknowledges packet 3 because that's the highest in order seek packet that it's received, all right? So it sends an ACK for packet 3, and the source then knows, oh, he didn't receive packet 4 because he's only ACKing packet 3, and I'm already up to packet 5. So he resends for that, and also he doesn't know that packet 5 actually made it through, so he has to, again, resend packet 5. All right. So this is more efficient from a time perspective. We don't have to necessarily wait until the timeout, especially if we have a large timeout for whatever reason. We don't have to wait for the timeout to know that packet 4 wasn't received. However, it does waste some resources because, as you saw in this case, we sent packet 5 was actually sent twice and received twice. All right. So any questions on this so far? Yeah.
That's really stuff that has to arrive in order, like streaming or stuff. Like for, say, downloading a file, would it have to arrive in order?
Okay, so the question is, yeah, does this only apply for stuff that has to arrive in order? Right, so you could think of, so the way I've given it here, it's for things that arrive in order, right? But you could think of ways to modify this to say, where this ACK could say, okay, I received 3 and 5, but not packet 4. And there are, there's many, many different extensions of this and so on. So you could do all these modifications, yeah. All right, so at this point, let's take a quick break to do. So at this point, we've covered the mechanisms to provide reliability, but we haven't covered is how you actually set up the connection between two hosts and negotiate these things like the sequence numbers of the packets and so on. So to do that, we do this thing called a three-way handshake. And a three-way handshake is, let me just draw it graphically. It's just to set up the connection. And what happens is the source sends a thing called a SYN, saying, hi, I'd like to open a connection to you, to the destination. Then the destination sends an acknowledgement of this SYN, so it sends a syn ACK. And then finally, because it's a three-way handshake, the destination, or sorry, the source sends a syn ACK ACK. All right. So very clever naming schemes. So could anyone tell me why three-way handshake and why not just a two-way handshake? Someone who hasn't answered the question yet today. Okay.
Verify that you can communicate in both directions. So
Exactly, yes. He said to verify that you can communicate in both directions. Because if we don't have this, so suppose we only had a two-way handshake. And so we send our syn, and then the syn ACK is lost. All right? Here, the source isn't really sure why this was lost. It probably thinks that its connection didn't reach it. Maybe it thinks, oh, this destination is too busy right now, so I can't do it. So it keeps sending syns and has no idea why it's not receiving the syn ACK. All right? And then if we only have a two-way handshake, the destination has no idea whether or not its syn ACK was received by the sender. And so it doesn't know whether to hold this connection open or what to do with it. And so it's not sure. So you have to, if you have these many different connections open, it takes a bunch of resources and so on at your server. So you want to avoid that. So we want this to actually say, yes, I did receive your acknowledgement of my connection. Let's go ahead and finish off the connection. Okay? So you really do need all three stages, and you can go through all the different cases and try and convince yourself that that's the case. All right? Okay, so we now know how to do reliability, how to set up a connection, but we don't know how to do is flow control. So the definition of flow control is that it's techniques to match a data source's sending rate, so a source's sending rate. And we want to be able to match a source's sending rate to the destination's receiving rate, okay? So I'll set the sending rate to the service rate of the destination and any network devices between the source and the destination. Okay, so what this means is, let me just give you another water analogy, and you can think of it as our source is a faucet dripping into, so this is our source, and it's dripping water into this bucket here. And this bucket has a drain on the bottom that drains away some of the water. All right? So what flow control does is it matches the rate at which we're putting water into this bucket to the rate that the destination can drain the bucket. All right, so the goal here is we never want to overflow the bucket, and we also don't want the bucket to run out because we always want some water to be running through there. Okay?
What if we have multiple sources?
Yeah, so now the question is, well, what happens when you have multiple sources? So we have another faucet here, and it's pouring in. And these two don't communicate with each other, right? This is the way it is on the internet. So we will look at this case, and when we have multiple sources, that's called congestion control, and we'll look at that next week. Okay? Yeah.
For the three-way handshake, could it be possibly justified with the same reasoning an N-way handshake?
Yeah. Okay, so the question is, couldn't you justify an N-way handshake? So I would go through all the cases, and you'll see that 3 is actually the minimum that you need. And so you want to go with the minimum, all right? But if you walk through all the different failure scenarios, you'll see that you need 3, okay? Okay, so back to this. So for today, we're only going to assume one source and one destination. And then next week, we'll talk about when we have multiple sources, because we want to start with something simple. Well, it's even not that simple with one source, but we want to start with something, you know, that's relatively easy to analyze, and then we'll move on and add more and more complexity, all right? So when we're when we're sort of thinking about, well, how are we gonna regulate this flow from the source and between the destination, we can try and optimize a few different objectives. That is, we want our flow control protocol to have these features. And one thing we'd like it to be is simple. All right. Then another thing we want is efficiency. And by efficiency, I mean minimal overheads. So for instance, this source could ask the destination with every packet that it sends, what rate can I send at next time? What rate can I send at, in the next couple seconds? And this adds some amount of overhead, right? Because we have to add that information to each packet. So we want to keep these overheads at a minimum if possible. Then we want it to be fair, meaning that if multiple people are sharing the channel, then they should each get a fair share of it, right? So we have a bunch of users sharing a link here. So suppose we have these 4 users sending across a bottleneck link like this. My picture's not great, okay. So we have these 4 people sending through there. Each of them should receive 1/4 of the total bandwidth available on that link, right? We want it, in other words, it should be fair. Everyone gets the same size slice of pie. Should also be stable. And by stable, I mean that it should converge to an equilibrium. So this equilibrium state just means that we don't want this source to have to constantly adjust its sending and receiving rate, right? It should be able to find a good rate and just send at that rate. And then if we do introduce a change into the system, like another user comes in and starts adding water to this bucket, then they should both converge to a new solution fairly quickly, all right? So when we're designing these protocols, these are sort of the things we want to keep in mind. And this is really, I know a lot of you aren't in engineering. So this is sort of what you do in engineering is you define the goals for whatever you're building, and then you explore the various trade-offs. Because no solution will probably be able to do all these things at once, right? Like, it's not really possible to construct as simple a solution as possible that's also, super efficient and fair and so on, right? We have to make these trade-offs. So that's what engineering is all about, and we're going to explore the various ways to design protocols that make trade-offs on these objectives, okay? All right, so there's a bunch of different ways to classify these techniques. And so the first classification of flow control techniques is called open loop flow control. Now, what we mean by this open loop is that there's no feedback between the sender and receiver. So they don't communicate at all about in order to do flow control. Now, the only way you can do this is with what's called admission control. And this is a scheme where you only allow users in who you know you have enough resources to fulfill their needs. All right, so what happens here is that a user asks for a certain, certain requirements. So let's just say for requirements, this is called a descriptor. It can contain things like bandwidth and latency. You can break bandwidth down. You can say, I want my average sending rate to be this, or my peak sending rate to be this. There's all sorts of different ways you could frame these requirements. But you ask for these requirements, and then the destination admits you or rejects you, okay? So it admits the request, or it rejects it. All right, so now because there's no communication, there's no feedback between the sender and the destination, once a sender is admitted, it's going to send at the rate you agreed on in your descriptor. It's going to send at that rate until it's done. All right, so a good example of this is, now I don't know, you guys might not have had to use dial-up growing up. If you didn't, that's fortunate. It was very painful. However, if you did, this is what it does in practice, is that your telephone company, or I guess your ISP, has a thing called a T1. And into that T1, they have a switch. And this switch has 24 incoming phone jacks. All right, each of these services a single customer. And so when you dial up, your PC over here, you have a modem attached to it. Since my PC looks exactly like the modem, I'll label the modem. All right, so your modem dials up, asks your ISP, do you have a free slot for me? And then your ISP, if it has a free slot, say yes, you can have this channel right here. And then you're plugged into this switch here they typically have 24 ports. And then you are guaranteed 1 out of 24th of the T1's bandwidth. All right, so for however long you want to use the internet, you're guaranteed a 24th of this bandwidth, all right? And so this isn't that efficient in practice because, when you're surfing the web, a lot of the time you're just idle. You're sitting there like reading a web page or something. So your 1/24th of the channel is wasted when you're just sitting there like reading a web page or something. And then also, if 24 people are already connected to this switch, then the 25th person will be rejected. And you just have to keep trying to dial up and dial up again and again until you somebody finally logs off, and then you get their spot. All right. So that's admission control. It is actually widely used. It's very simple, but it doesn't meet really, it's not very efficient. It is fair and it is stable, but it's not efficient at all. All right?
I thought the switch is a physical thing.
Yes, the switch is a physical thing.
So how do you actually get a port?
Yeah, so I'm skipping over a lot of details here of how you actually, right. So the question is, how do you get a port on this switch? Right, so you do need a middle box here that actually knows if this has free ports and so on. So I'm just skipping over that. Just assume that the switch can give you a port if it has one free, okay? But you will learn that later on. Okay. All right, so now that we've learned the simplest type of flow control, let's look at something more interesting, and this is called closed loop flow control. Now here we actually do have communication between the sender and the receiver. So the sender and receiver in this case actually dynamically decide on a sending rate. All right, so in open loop flow control, the sending rate has to be negotiated ahead of time. All right, you contact each other. You say, "I'm going to send you this much data at this rate," and then you are statically those resources are reserved for you, and they're statically allocated to you. But here we do this flow control dynamically. And it's done dynamically because the devices do not actually have enough bandwidth or enough resources to support transmission of everyone at their full rate, okay? So the devices do not reserve enough bandwidth for communication. Okay, and this phenomenon where the devices do not reserve enough bandwidth, this is called statistical multiplexing. Because we are multiplexing that channel with multiple users at the same time. All right. Now within closed loop flow control, there's a few different ways we can actually go about achieving the flow control. So the first is where we use explicit notification of the sending rate and the status of the network. So let's just say network devices use explicit control messages to negotiate the sending rate. Now what I mean here by these explicit control messages is that these are actually put into the headers of the packets, all right? So that means if we send a packet here, we have the data, we have the header. In the header, there's some field that says, you know, for instance, is there congestion in the network? All right, we'll look at that a little more. Let me give you a couple examples of protocols that are explicit feedback protocols. So the first one's called stop and wait. And this is one of the simplest flow control protocols because all you do is you send a packet, you stop, you wait until you receive an acknowledgement, and then you send another one. Okay? So it looks like this, where we have the source, the destination. Then the source sends one packet. Now he doesn't do anything until he receives an acknowledgement. All right? Once he receives the acknowledgement, he can send his next packet. Now, if an acknowledgement is lost or a packet is lost, then he has to rely on a timeout. And after this timeout, then he resends the packet. All right, so you can see that this isn't that efficient, right? Because I have to wait until I get this acknowledgement before I can send the next packet. And so I'm never going to be able to make full use of my bandwidth between the sender and the destination, right? Now let's generalize this a little bit. So the stop and wait, this is sort of one of the earliest methods of flow control because it's really simple, but we can generalize it pretty easily to a static window. And actually, before we go into the static window, let's take a quick break. Okay, so before the break, we left on this major cliffhanger of what's a static window protocol. And a static window protocol generalizes this stop and wait protocol. So instead of just sending one packet at a time and waiting for the acknowledgement, now we send let's send W packets before receiving acknowledgements, okay? So now we send W packets before waiting. Now this W here, this is what's called a window. So we'll call it the transmission window. And the transmission window, yes, I know it's morning, but bear with me. The transmission window is equal to the number of packets, number of unacked packets you can have. Okay, so if we look at the picture of this, let's say for this example that W is equal to 4. That means that now the source can send 4 packets at a time, and it doesn't have to wait. And then once it receives this acknowledgement, let me redo that in yellow here. So it keeps track of how many unacked packets it has. So now it has 4 unacked packets. That's its window size. That's the most it can have. As soon as it receives this ACK, then it can send another packet. Okay, because it can always have 4 unacked packets out at once. And so now if this ACK is really delayed, it takes a long time to get here, then it cannot send another packet until it receives that second ACK, okay? So are there any questions about the stop and wait protocol or static window protocol?
Doesn't the static window decay into like the stop and wait if the buffer's always full, like if W's always at that peak?
Okay, so the question is, doesn't the static window just sort of degrade to the stop and wait if your buffers are full, like if you're dropping packets and stuff? No, because here we don't dynamically adjust this window size. We keep this window size static, right? So this means that we have to sort of have a little bit of information about our network in order to set this window size. Because if we know that our round trip times are long, that it's going to take a really long time to get to the destination back, but we know that there's not much error happening, not many packets will be dropped, then we can set our window really large because we know that not that many packets are going to get dropped and it's going to take a really long time to receive an ACK, so we should send a bunch of packets and not have to wait too long for the acknowledgements, okay? So this is why this isn't a good protocol, is because setting this static window size is really tough. All right? Yeah.
Is this a type of stop and wait protocol or is it a protocol?
It's a type of stop and wait protocol, yeah. It's just, it's just generalizing it. Here, this original stop and wait, W is just equal to 1, right? Yeah.
I was trying to ask, are these all follow the closed loop flow of the window?
Yeah, these are closed loop. Yeah.
So how does this tie into the cumulative acknowledgements that we talked about?
Right, so we're going to look at extending this. For right now, this doesn't use cumulative acknowledgements, but we will extend it to use cumulative acknowledgements next, okay? But any more? Yeah.
Yeah, sorry. I'll ask you a question to know, like, what's the difference between closed loop and open loop?
Okay, so
Two terms.
yeah, so open loop, the sender and the receiver do not have any feedback between each other about their rate, okay? They set up the connection, and then that's, once the receiver has said, okay, you can send to me at something like 1 megabyte per second, then you just send at that rate. You'd never change sending that at the rate.
One time, and I'll take that one time.
Exactly. Whereas in these closed loop flow controls protocols, there's communication about what the sending rate should be. All right, now here we're not dynamically adjusting how many, like our window size, but the sending rate is dynamic because, so in this case, this this acknowledgement took a really long time to receive there. So our sending rate dropped because this acknowledgement took a long time to arrive, okay? Yeah?
So we have to wait for all four packets to arrive before we send the acknowledgement back?
No, you acknowledge each packet. All right, so here, this first packet arrived and he acknowledged it.
Oh, okay.
Second packet arrived, he acknowledged it. Third, acknowledges. Fourth, and so on, okay? So it's the point is to, okay, so we can do error control with this. Now we can ensure reliability, right? And we do flow control because, so let me just draw an example of how this does flow control. All right, so we're sending some packets here, right? And these are acknowledged. So let's assume everything goes smoothly. That round, now we send here, and we're sending a little too aggressively, so this packet's lost, right? So it doesn't get acknowledged until the timeout happens. So once this, let me call this packet 5. Once packet 5 times out, then it'll be retransmitted. All right, so because this was lost, then we had no communication on the channel until the timeout occurred, right? So that meant that we were sending really fast. We got the ACKs pretty quick, so we tried to send really fast again. Then our packets were dropped, so we backed off our sending rate. We waited a little bit, and then we tried again. All right? So these timeouts introduce these waiting periods, which slows your overall transmission rate.
Does the timeout guarantee that the packet is lost?
No, it doesn't guarantee that it's lost, right? Because you could imagine a scenario where this packet actually receives, it sends the acknowledgement, but it takes a really long time for some reason. And the acknowledgement actually gets there, but in the meantime, we've timed out and sent the packet again. Okay? Yeah.
Another case where packet 5 was dropped, wouldn't it just try and resend packet 5 like immediately again because it still has like 3 it's already gotten 3 acknowledgements?
Yeah, so in this case, yeah, so this is a good question. So it was like, well, when did it just resend? It got this acknowledgement for packet 6. So when did just, or sorry, for a different packet. So when did just send it immediately? And the answer is there's different ways you can do it. You can rely on the timeout, or you can rely on these receiving acknowledgements for, future packets or packets that you haven't already received an ACK for. Okay. So we're going to look at all these different ways in much more detail next time. Today, I just kind of want to give you guys a high-level overview of the different ways you can do flow control, and then. So TCP does a lot of these different variants, and there's all sorts of different variants on TCP. So we'll look at all the different ways to do this stuff next time, okay? Okay. So let's look at one other way to explicitly do flow control. And this is where we have explicit congestion notification, all right? Now, what explicit congestion notification means is that there's a bit inside of each header, each packet header, and this bit indicates whether any device along the path is overloaded. All right, so it indicates. We'll call any overloaded device, we'll say is congested, okay? So it indicates congestion. Meaning that if we have a PC here, it's our sender sending to a router, which then sending to another PC. If we send a packet, we have the data, remember, we have the header. In this header, as I mentioned before, we have an explicit box here that says, is there congestion or not? So the sender initially sends this packet out with a 0 in the congestion box, right? There's no congestion in the network. Now, if this router is congested, meaning that its buffer, so I should redraw this just a little bit. So we place that into a buffer, right? So if this buffer is almost full, then we know that there's congestion at this router, right? So let's suppose that our packet comes in here. It's the last packet in this buffer. So now this router will set that congestion field to 1 to say, yes, there is congestion in the network. It goes on to the destination, and the destination does not modify this field, okay? Once the congestion field has been set to a 1, no other devices change that. Now so let's do the messages that way. The reply comes back and it keeps this congestion field intact. All right, so it still has the 1 in the congestion field. All right. Now, once the sender receives this acknowledgement with the 1 in the congestion field, it knows it needs to back off and send at a slower rate. Okay? So I'm not going to go into any detail about when do you decide to set this congestion bit to 1 and how much do you change your sending rate and so on. If you receive congestion, you can go into a lot of detail about that, but all I want you to know is this concept of adding a bit to the header to explicitly indicate congestion in the network. All right? So any questions on that?
In the homework, we were checking the network diagnostics and stuff. I think it came back with a 2 for congestion. I mean, like twice.
Okay, so yeah, the questions in the homework you could check for congestion, and there was, you know, this field didn't have just 0, 1, it was 0, 1, or 2, right? So you could imagine that, you know, this is just one bit of knowledge, but you could make that more, right? You could have, I don't know, up to 1 million or whatever level you want to indicate, like there's really a lot of congestion here, or there's just a little bit, and then it tells the sender how much to back off. Okay. Yeah.
What happened if that packet containing the congestion bit got dropped for some reason?
Right. So the question is what happens so this gets dropped, or the acknowledgement, or here gets dropped. Yeah, and that's a difficult problem. You have to use things like, I mean, you sort of need some implicit assumptions like, oh, a timeout means that a packet was dropped. Yeah, so there's different ways to overcome that. We're not going to go into that level of detail. Okay, any more questions on that? All right, so before we end, let me just briefly introduce you to implicit congestion notification. So this is implicit flow control. And in implicit, we're going to dynamically adjust our flow window. All right, so our transmission window. And we dynamically adjust it in response to undelivered packets. Okay, now how do you notice that a packet wasn't delivered? We'll do the same tricks. We use these timeouts. We'll use the sequence numbers and so on. For now, I'm just going to assume that you can notice when a packet isn't delivered, all right? And then next time we'll go into how to actually, what that actually means and more what to do about it. Okay, so TCP has a dynamic window, right? So that means that now this W is no longer fixed and we adjust it on the fly. So at the beginning, we started out at 1, meaning that we can send 1 packet before receiving the acknowledgement, right? We can have 1 unacknowledged packet out there. Then we started at 1, and then in the beginning, we do this thing where we exponentially increase our sending rate each time we receive an acknowledgement. So for each acknowledgement we receive, we double the window size. And we double it until we reach some threshold. So once W has reached this threshold, we move into an additive increase phase. So the next phase, and by the way, this stage here, this is called slow start. So once we reach that threshold, now we increase the window at time t is equal to the window at t minus 1 plus 1 divided by the window at t minus 1. All right, so this is each time each acknowledgement, we increase our window by this much. So we increase our window additively like that, all right? So what this looks like then when we're transmitting data is across the bottom here, I have time, and the y-axis, this is our window size. All right, so we start out at 1. So we start out sending at a very low rate, but we double that each time. So we're growing, sorry, I drew that the wrong way. So we're growing exponentially. All right, and then we reach some threshold, and we change into this additive increase phase, where we increase like this. And now we need to decide, suppose that here we have a packet loss. Now we need to decide what to do once we have a packet loss. All right, and we'll go over that next time.